Assalamualaikum warahmatullahi wabarakatuh. My name is Nurrafidah binti Razak, and today I will present to you my thesis project, which entitled Electrical Conductivity Performance of Modified Lanthanum Strontium Cobalt Ferrite m-LSCF towards Proton Conductivity Fuel Cell. And the supervisor who is supervising me is Dr. Razila Rajmi. In this presentation, there will be 4 parts involved, which are introduction, methodology, findings, conclusion, and recommendations. Let's move to the first part, which is the background of study. A solid oxide fuel cell (SOCF) is an energy conversion device that generates electricity by electrochemically mixing a fuel and oxidant over an ionic conducting oxide electrolyte. In other words, SOCF are a form of fuel cell in which the electrolyte is made of solid oxide minerals. SOCF works in a very high temperature, which are in the range of 500 to 1000 degrees Celsius, which makes SOCF does not require any other costly platinum catalyst. SOCF is the most common one due to its high performance, as it is more fuel flexible due to its ability to reform hydrocarbon fuel internally and tolerate some degree of common fossil fuel impurities, according to Alas White. On the other whole, there are a few types of fuel cells, yet all of it uses the same process. Let's talk about the part in SOCF. The parts involved in SOCF are negative electrode, which are called as anode, and a positive electrode, which are called as cathode. In between those two, there are an electrolyte that undergoes an electrochemical reaction to produce electric current. Now let us proceed to the next part of the introduction, which is LSCF. Lanthanum strontium cobalt ferrite (LSCF) are the most studied cathode for intermediate temperature SOFC, as LSM lanthanum strontium manganite peroxide are reported used for high operating temperature. However, LSM cannot operate at low temperature due to its high activated energy, which will increase the polarization resistance and decrease the catalytic activity. Hence, a new cathode material of mixed ionic electronic conducting (MIEC) materials are obtained from peroxide-based materials such as LSCF, barium strontium cobaltite ferrite (BSCF). LSCF is a peroxide-based material that are suitable to be used in intermediate temperature SOFC. The reason why LSCF is suitable is because of its good features, such as chemical and thermal stability, strong catalytic activity for oxygen reduction, and high electrical conductivity. After comparing LSM, LSCF, and BSCF, LSF showed that it is the most reassuring cathode material. The chemical stability of LSCF is the main reason why it is used in intermediate temperature of SOFC. Even though LSCF comes with a lot of advantage of such as good electrochemical performance at low temperature, the existence of cobalt in the MIEC material increase the thermal expansion coefficient of cathode, which lead to the incompatibility with electrolyte. Due to that, various cobalt-free materials have been developed. Another drawback of LSCF is the degradations of the cathode that is caused by the phase decomposition of LSCF within a 15 nanometer thick surface region. The degradations also occur due to the Si contaminants that are accumulated in the cathode of SOFC stack over time, and the strontium segregation that occur on the cathode surface and the interface of electrode and electrolyte. As mentioned before, due to the Si contaminants that are accumulated in the cathode of SOFC stacks over time, surface segregation occurs in LSCF. SR surface segregation, which is known as strontium surface segregation in LSCF, has been reported by a few groups. Strontium is a very active element in LSCF. Strontium is reported to diffuse out from bulk of cathode to the surface and react with Y as Razak to form insulating strontium zirconate phases. The strontium-rich phase can be intrinsic and also be activated by presence of impurities. Strontium segregation increases as the temperature increases and also when the oxygen partial pressure increases. However, experiments need to be done to clarify how strontium segregation is influenced by the condition stated and how the surface modification of LACF cathode material is proposed in improving its stability plus reducing the surface segregation. The strontium excess in the form of oxide that was observed on the surface of LACF cathode. As reported by Zhang in 2012, the amount of strontium oxide increases as the temperature or the oxygen partial pressure increases. Surface segregation or kinetic demixing are also related in segregation due to a chemical or electrical potential gradient. Surface segregation or kinetic demixing in LACF influence oxygen exchange kinetics, electrochemical activity, and also cation diffusions. Preparation of BCZY. The citric phase were used for BCZY powder synthesis on nitrate barium, cerium-3, and zirconate for hydrogen. The stoichiometric concentration of nitrate 3YNO3 were weighed and dissolved into 150 ml of the ionized water in beaker A and then stirred. Citric acid Ca then added with constant stirring overnight. A further beaker, which is known as beaker B, were filled with 200 ml of ammonia followed by ethylene diamine tetraacetic acid, which is known as EDTA. The solution was stirred overnight. After the polymerization process, that the EDTA and ammonia in beaker B is eventually added to the metal nitrate and Ca and ethylene glycol, which is known as EG in beaker A, which act as the polymerizing agents. After 24 hours of mixing, the pH meter was used to obtain a neutralized metal complex solution, which is at the pH meter of 7, by adjusting the pH value with concentration ammonia. After that, the solution was heated and stirred for a few hours on a heating plate at 120 degrees Celsius. This is to get rid of water until a brownish gel is obtained. The gel was dry and pre-calcined at 325 degrees Celsius for a span of 2 hours and then calcined at a temperature of 1100 degrees Celsius for 10 hours with a rate of 10 degrees Celsius per minute. I have showed you the synthesis steps of the electrolyte powder on my right. Next is the sample preparation of the green pellet BCZY. An electronic balance were used to weigh 0.65 gram of BCZY powder with 4% of nickel oxide that act as sintering aids. The powder was placed in a cylinder pellet and pressed for 3 minutes at 5 tons. A two-step sintering procedure was carried out with pellet electrolyte BCZY of 13 mm diameter and 2 mm thickness. The pellet was put under the palm before the sintering process to avoid sticking. The pellet electrolyte was sintered in the primary air at 1500 degrees Celsius for about 1 minute, and the second stage where the electrolyte was sintered for 12 hours at 1450 degrees Celsius. These are called two-step sintering. In order to quantify the sintering density, the mass, diameter, and thickness of the pellet are registered before and after sintering operation. The pellet were polished such as the surface is flat and smooth with thickness of 0.8 mm. I've showed you the flowcharts of the preparation of the green pellet BCZY. Next is the binder preparation and spin coating method. The binder were prepared by mixing 0.05 to 69 gram of ethyl cellulose and 1 ml terpianol. The stoichiometric quantity of BaNO3, ZrNO3, and YNO3 were weighed and dissolved in 150 ml of deionized water. The solution was stirred overnight. The cathode slurry were prepared by combining 0.5 gram of LACF cathode powder in a binder solution. The cathode slurry was placed into the sonicator for 1 to 2 hours. The surface of the BCZY was painted by the cathode slurry using a spin coating technique. The pellet was covered 3 times on each surface. For each spin coat, the pellet was heated for 10 minutes at approximately 100 degrees Celsius. The pellets was heated at 100 degrees Celsius overnight, followed by fire at 600 and 900 degrees Celsius for 1 hour and 3 hours respectively. This is done to allow a good contact formation between electrode and electrolyte layers. I've shown you the flowchart of the binder preparations down below. The last step of the sample preparation is surface modification. There are 2 types of LACF pellet made. One is pure LACF while the other one is submerged in ZrOCl2 8H2O with a temperature of 80 degrees Celsius. The temperature is to ensure that the excess of strontium are removed to modify the surface with metal cation. Approximately 0.46612 gram of ZrOCl2 8H2O added to 100 ml of deionized water. The solution was then poured into a volumetric flask which can sheet well to ensure its homogeneity. The pellet was submerged in the solution for 2 minutes. The submerged pellet would then dry out at a temperature of 100 degrees Celsius for 2 minutes in the oven. Next, all 2 pellets were coated with platinum, which will platinum act as the current collector. The pellet was heated to 100 degrees Celsius for each coating in the oven, approximately 10 minutes. Then both pellets were sintered at 900 degrees Celsius overnight to make sure the substance with platinum is dry entirely. The pellet were polished with sandpaper to extract the platinum coating around the pellet after the sintering process. This is to make sure there is no electron can flow over the side of the pellet during the measurement. Before and after polishing, the multimeter were used to check the pellet resistivity. As you can see from the picture, the one on the hot plate is when the pellet are submerged into ZrOCl2 8H2O, while the one on the left is the pellets that have been dried out. The first thing in the finding is the area specific resistant ASR or modified LACF symmetrical cell. The area specific resistance of the ohmic losses ASR is the direct measurement of the interface performance. The best fitting line is determined by using the modeling tools at the Siemens software. Before the modeling was done, the bad data are removed in order to obtain an easy interpreted graph. 3 arcs consist of LSRS1, RSR1, R1Q1, R2Q2, R3Q3 were used for 700 degrees Celsius, and 2 arc model were used at 800 degrees Celsius is LSRS, R1Q1 and R2Q2. Area specific resistance are then calculated by using the formula of Rp times with S divided by 2, where the Rp stands for polarization resistance at the interfacial layer of cathode electrolyte, and S is the surface area of the pellet. The polarization resistance Rp is also defined as the sum of R2 and R3. As you can see from the graph on the left, there are 3 arcs, which mean that these graphs are for the 700 degrees Celsius, which consists of 3 arcs. The difference between the 2 graphs can be seen at the number of arcs. As for 700 degrees Celsius graph, as mentioned, there are three arcs plotted, which are R1, Q1, R2, Q2, R3, and Q3, where each arc represents a process. In R1, Q1, it represents an electronic range transfer at the cathode surface, while in the R2, Q2, represent the ionic charge transfer at the cathode, and at the last arc, which is the R3, Q3, it represents the charge transfer operation such as oxygen ion diffusion in the cathode bulk and oxygen ion incorporation from the three phase boundaries. The R1 correspond to the electrolyte response, while the R2 and R3 correspond to the cathode processes. The R1 have a higher frequency arc correspond to the contribution of BCZY electrolyte, while R2 and R3 are assigned to charge transfer reaction, which is the transfer of proton from the electrolyte to the electron. This is the 800 degrees Celsius graph, which consists of two arcs. As mentioned before, by using the equation mentioned, the value of area-specific resistance of ASR is obtained. The value of ASR obtained for 700 degrees Celsius is 0.243 ohm centimeter squared, and the value of ASR for 800 degrees Celsius is 0.1230 centimeter squared. The value obtained can be considered as a good value, as it is in a lower range. The next part in finding is the LSCF microstructure by using SEM-EDX. One of the methods used to overcome the degradations due to strontium segregation is by deep coating of LSCF surface with layers of ZrOCl2 8H2O. This cathode microstructure still preserved after surface modification process. The elements that have been disabled are aluminium and bromine. The elements that appear on the palette shows that the palette analyzed is a BCZY palette. This is proven as the oxygen weight concentration is higher, which also means that the surface is not stable. Another proven that this is a BCZY palette is the existence of barium, cerium, zirconium, and yttrium elements. Next is the microscopy images of BCZY LSCF. The oxygen weight concentration are higher compared to the BCZY palette. This is because the palette are submerged into ZrOCl2 8H2O. The Zr4+ is an addictive cation that is binary oxide, have higher enthalpies of oxygen vacancy formation compared to LSCF. The less reduction cation Zr4+ is also found to improve the oxygen exchange kinetics and stability on LSCF. It also shows that the reducible cation increase the oxidation state of CO and on the LSCF surface and decrease the surface oxygen vacancy concentration, which then will lead to a smaller electrostatic driving force of strontium segregation. In the methodology, it is mentioned that the pellet is submerged in ZrOCl2 8H2O in the temperature of 80 degrees Celsius. This is because it is needed to ensure that the excess of strontiums are removed and the surface are modified with metal cations. Also, it is done to ensure that the surface exchange kinetic does not degrade to a very huge extent compared to the initial surface oxygen exchange. Microscopy images shows that the correlations of the electrochemical stability to the surface chemical stability. The result proved that the addition of the less reducible cations Zr4+ prevents the segregation of insulting strontium-rich phases and also improves the electrochemical stability. There are a few elements that have been disabled from this palette, such as aluminium, gold, bromine, niobium, and titanium. Moving on to the last part of this presentation, which is the conclusion. To conclude, in this study, the area-specific resistance ASR obtained is the direct measurement of the interface performance. The ASR obtained at 700 degrees Celsius was 0.243 ohm centimeter squared, while the ASR obtained at 800 degrees Celsius is 0.123 ohm centimeter squared. The EIS measurement gives three impedance responses, which are grain boundary response, interfacial operations, and also cathode reactions. It shows that the pellet have high zirconium atomic and weight concentration, which is 5.77 mol per meter cube. This is because the submerged pellet undergoes surface modification. Both pellets were coated with platinum, which acts as a current collector, which directly improves the electrical connection between the cathode and internal and external instrumentation. The platinum serves as a good interfacial electronic conductor. The BCZY-LSCF, which is known as the symmetrical cell, were modified through surface modification by using ZrCl4+, aqueous solution. This is done by deep coating method, where the result shows that the ZrCl4+ aqueous solution have the ability to reduce oxygen vacancy on the surface. Deep coating method plays an important role in the surface modification, where the pellet is submerged into ZrOCl2 8H2O. Lastly is the recommendations. Despite the progress made in studying the electrical conductivity of the LSCF cathode against a proton conducting electrolyte BCZY in the symmetrical cell of LSCF BCZY LSCF at a temperature ranging from 700 to 800 degrees Celsius, there are still a lot of aspects that need to be further investigated. First is the temperature that can be increased from 500 to 800 degrees Celsius with 50-50 intervals, which allow us to obtain varieties of results during data collection. Next, in order to achieve a more accurate result, the concentrations of ZrOCl2 8H2O can be increased from 20 millimole to 25 millimole and increasing the heating process to higher than 80 degrees Celsius. Intensive work are still in progress to further investigate the performance of LSCF BCZY LSCF cell by using another type of dispersion agent and composite cathode of LSCF BCZY. Thank you so much for your time, and thank you for watching.